Okay, guys. So let us start the stream. So for first question, we are given with an array a1 to an of n integers, and we can do one of the operations of this form, like choose a sub array and then replace it with an mex of that. Those who don't know what is mex, so mex is a minimum excluded element, where it's the smallest number which is not present in the given array. So now let us take the cases where the answer would be 0. If any one of the element is non-zero in the array, then answer can't be 0. And if all of the elements are 0, then the answer must be 0, because we can't have answer less than 0. Now consider, let's take a case of 1 as the answer. So answer will be 0 if all the elements are 0. Even if one element is present, the answer must be at least 1. Now let us suppose take an example of array. Uh, so here in one operations we can't make the whole array 0, because if we choose to pick the first element, then the second element we can't pick. If we pick the element 0 in our subarray in that only one operation we are choosing, then it won't remain 0, as the mex of any subarray that contains 0 is at least 1 or greater than or equal to 1. So in one operations, if we are making the whole array 0, then all the elements that we are picking must be 1, and we also must pick all the elements that are not equal to 0. If we don't pick any of them, then the mex will, the whole array after transformation will not become 0. So so we have to pick all the elements that are greater than equal to 0, greater than 0. And if we can't do such a thing, then we can't do in one operation. So let's suppose if we have some trailing zeros and some leading zeros, then we can pick the middle segment and make the whole array in one operation all 0, else we can't. We also don't need a trailing zero, like if there are no zero if there are 0 or more than one zeros, then we can pick. And similarly for the leading zeros. So if we remove trailing zeros and leading zeros, and we get a array with all elements greater than equal to 1, then we can successfully say that we can do in one operations. and since we have at least one element which is not equal to 0, we can't do that in 0 operations. So answer would be 1. Now let us say answer for case 2. If we choose all elements of the array, no matter what the elements are, and then again choose it will become some number, let's say x. And now if we choose again this element x, it will become 0. So that is some element which is not equal to 0. So here I am considering case where there is at least one 0 in the array. So if we pick the whole array 0, and therefore the answer would become which is non-equal to 0, because mex doesn't contains the element which I have included. So now if I convert take again the transformation of the whole array, then it will definitely become 0. So we can always do any array in two operations, and if there is no 0 in the array, then we can do in one operation. So answer must be 0, 1 or 2 depending on the case. So now let us see the code implementation of this. So basically here I have taken the two cases where if all elements are 0, then this case else will trigger. If at least one element is also non-zero, then this if will trigger. Okay, now let's say if we have at least one element which is non-zero. Now there are two options. Either it answer will be 1 or answer will be 2. So if we remove leading and trailing zeros, which I have done these 4 lines, these 5 lines, then if we get an array which doesn't have any zeros, then we can say the answer would be 1, else the answer will be 2. Okay, so this solves the problem A. Now let us jump to problem B. So problem B is PS. So now we have to do some observations here. Let us suppose if we have a case where we have P before S. So what does this tell? That this is a permutation, and this is also permutations, where this is an array. Since both are permutations, both should contain 1. But since the whole array is also a permutation, both of them can't contain 1. So there is a contradiction. So P can't be before S. So this is first observation. Suppose there is a dot here. Wait. Second observation we can make that the first and the last element is equivalent to having dots. So if we have the last element P, then it is equivalent to having last element as dot only. Why? Because the last element P says the condition that the whole array is a permutation, but we already know that. So we this doesn't give any excess information. So we can convert the last element to dot. Similarly, if the first element s, then we can convert the first element also to the dot. Now suppose uh, okay, now suppose 3, we have some dots, and since we can't have p before s, we take s before p. So this tells us that the whole thing this is a permutation, and the whole thing this is a permutation. Now suppose without loss of generality we have this arrays as 1 2 3 4. So now consider element 5, and if we speak generally, then let's say the total from before any, take any s and take any p, and let there be k dots there, and consider the element k plus 3. So we have two options to put it. We can put either k plus 3 element here or k plus 3 element here. Why can't we put between? Because if we put it in between, then we will have to drop any one element which is from 1 to k plus 2. And since this both arrays are permutations, the array that is colored in red and that is colored in blue, sorry, violet. So this, since this both arrays are permutations, this both arrays should contain all elements up to 1 to k plus 2, because these arrays are greater than equal to length of the length of these two arrays are greater than equal to k plus 2. Therefore all the elements should be present between them. But uh, if we take the k plus 3 element here, we can't put any with, without loss of generality, let's say 2. So if we 2 is put anywhere at the side, then one of the array must not have that element 2. So this is a contradiction. Now let us say if both element arrays have 5. Why should they both have 5? Because the length of this array is greater than equal to k plus 3 also, and this array is also length greater than equal to 3. So this element, this both of these arrays should have k plus 3. So there is a space for k plus 2 elements, and we want to have k plus 3 elements fit into that. So by pigeonhole principle, uh, we can't do. So if we have a space, then s, then p, then space, then it is not possible, so answer will be no. So what left is, so p can't be at the right, because we told that it is equivalent to having a dot. Suppose we have p at the left. So what does this means? That this is a permutation of length 1. So this first element should be 1. This means that there can't be s, because if there is a subsequent s, then uh, we can't, we have to replace it. We have to put 1 in that suffix array. So we can't have any s if we have p at the starting position. Now consider a case where s is at the end, then we can't have uh, p before, since 1 must be at the last element, and since if we have p before, then 1 must also be in the uh, prefix subarray. So this also can't be possible. So let us compile all the cases in a neat fashion. So if we swap last p with dot and first s with dot, we can have only either all, either p or s. This is the final conclusion of this whole case work analysis. If you didn't get it, you can rewatch this, thinking this in mind, and then do the rewatch the case analysis I have done earlier. Then you will get it. So let us understand this in code. So we have taken input n and s, and according to our simplified case analysis, we will remove the last p and first s as they are not relevant. And now if we check that the answer of p equal to 0 or answer of s equal like count of p equal to 0 or count of s equal to 0, then we are sure that at least one of them is not present. And if one of at least one of them is not present, then we guaranteed answer yes. And by case analysis I have done before, if both of them are one, then the answer must be no. So this should be the code. Now let us hop on to the problem C. What does this problem tell? That you are given three integers n, x and y, and you have to construct an array a 1 to n such that if x is friend with y, then then the mex of all the friends is equal to that same value. So first observation, the array values can't be greater than 2. Why? Let's suppose we have 3 here, and there are only 3 friends of them. So okay, if all are different, okay, forget it. So this is constructive algorithm problem. So we will take a case where we randomly put the arrays. Let us first take the case where n is even. So and we alternate 0 1 between all the values. Now suppose some x and y are connected and they both are different, then we can clearly see that arg- this argument will work for the n equal to even and x uh, and y doesn't have same parity. Now let us suppose x and y have same parity, but n is even. So let us see these both are connected. Sorry, these both are friends. Now since this element has mex1, but its friend is also 1, so this mex is 2 and not equal to 1. So let us change it to 2 and see what happens. So for all others, nothing has changed except the star ones. Star one with zeros have nothing to worry, because if any of the if all of the friends are not equal to 0 and they themselves are 0, then the mex validity holds for them. Now let us check for one. Um, two friends are zeros and one of them is 2, so uh, the mex is 1 and which holds for him. For let's say for 2, check for 2, then we have two friends with 0 and one friend with 1, so the mex property hold also for 2. So this has no issue if n is even. And okay, wait a minute, let us also connect on the zeros for sake of completion. Um, so now this will become 2, and again let us check if any of the mex fails. So if we check for 2, we have 0 1 1, so mex is 2. For 0 it's 1 1 and 2, so mex is 0. For 1 it is 2 1 and 0, so mex is 1. For this one also it holds, so nothing issue in this. Now let us construct another case where n is odd. So we will have some issues like this. Two friends which are adjacent but have the same value, which can't be true because both of their mex will turn to false. So let us change one of them to 2 and see what happens. So now all of the mex properties are satisfying, which you can see by brute force. Now let us say if two non differents are connected, let's say 2 or 0 or 1 or 1 or something like that, then also it won't break anything, because the for mex, if we add some elements which is not equal to the original element, the mex will not change. It can either increase or stay the same, and to increase we have to connect same elements. So let us connect 1 and 1. So what will happen? There will be at least one of the ones which is not directly connected to 2. Why? Suppose this one is also adjacent to 2. So this 2, and there is only one 2. So this 2 must have adjacent to both ones. But if that was the case, then we could simply have written it as 0 and no conflicts was there. We have wrote the 2 because there was conflict. So if we have the necessity of writing it 2, then at least one of the neighbors is 0 and exactly one of the neighbors is 1. So if there are two ones, so both can't be adjacent to the 2. So one of them will not be adjacent to 2. Let us change that 2, 1 to 2. So now let us see if all the properties are holding or not. So for this 0, we have 1, 2, so this is holding. This 0 also holding. This 2 also holding because we have 1 here. This 1 also holding and this 2 also. So our answer will work for this only. Now let us see if two zeros are connected, what will happen. And if we change this to 2, then and suppose there are no zeros, let us see this case. So for this one, both of his neighbors has become 2. So for 1, it is this problem. For 0, if no one is no none of his neighbor is 0, then it's hold. For 1, none of his neighbor should be 1 and at least one of its neighbor must be 0. But here that doesn't apply because both of his neighbor are 2. So max here would be 0, but it is 1. So what we can do, we can change it to 0. And now this will not hold true. So instead of doing this, what if we replace all ones by 0 and all 0 by 1 at the beginning, so that there doesn't exist a case where two ones are connected. If we flip here only 0, 0, 1, 1, 0, 0, 1, 1, then always there will be edge between two ones or at least one one. So if that is the case, then we don't have to worry. So let us see this in code. So here we have taken the input and subtracted 1 to make it 0 index. Now we have wrote an array of alternating ones and zeros. Now if we see that both the values are already zeros, then we flip that to make that case false. Now if we have 0 and 1 adjacent to each two ones adjacent to each other or two zeros adjacent to each other, we will make one of them as 2, as we see in the case of the odds. This will trigger. Now let's suppose if ax is not equal to ay, then we have to do nothing. But if ax is still equal to ay, then we know at least one of them must be 1. And the case where uh, if any of them is adjacent to 2, then we won't change that element, else we can change arbitrarily any of without loss of generality. Let us change x, and if x is adjacent to 2, then we won't make it 2. And therefore since if x is adjacent to 2, y must not be adjacent to 2, then it will hold. So by case analysis this problem is also solvable. So we observe that all the three problems here are very case analysis, and the problem D is DP onwards, and which will be discussed by someone else.
Hello, am I audible?
Yes, you are audible.
Okay, thank you. So we start with problem D. In this problem, we have a grid of n rows and m columns of non-negative integers and an integer k. We have to reach from cell 1, comma 1 to cell n, comma n, and in every step, we can either move down or right. That means we can either increase I by 1 or j by 1. So um, once we go from cell, once we visit a cell, we have to like add some cost. Like let's say we visit a path and the sum of numbers of cells on that path is y. Then we incur a cost kx plus y. Here kx is a term for we have an operation that we can pick any row and cyclically shift to the left by one. So we look at the constraints. We have n comma m less than equal to 200 and summation of n times m less than equal to 5e4. So so our task is to do operations in such an order and visit paths in such a way such that this cost is minimized. This seems like a dynamic programming task. We can let d of I comma j equal to min cost to reach cell I comma j such that shift operations are done only on rows less than equal to I. That means we can do the operation on the remaining rows after this. So let's say we have reached cell. First, we make a base state. For that, we can append a row in the beginning and start from this cell, and let all others to be infinity so that we cannot start from there and visit the first cell of the second of the first row with this cell. So would be our base state. After that, we have to define the transitions. For that, we can rotate the next row multiple times. We have m ways to do that. So we'll rotate the row m times and calculate the TP sets for each rotation. So let's say that after k rotations, the next row looks like a a1, a2, a3 to an. K is already in the input, so let's use another variable. Let's say we do L shifts. So let the DP states of the previous row be D1, comma D2, comma till Dn. Sorry, M. There are M elements in a row. So the transitions can be like we go down from D1 and then some right, or down from D2 and then some elements right, or down from some DI and then some elements right. So for that we will iterate from first element to the last element from left to right. We will let the new DP be defined as ND. We will have ND1 equals D1 plus A1. We will have ND2 equals either we go from here to here or we go from D2 to A2. So for the first case, the cost would be ND1 plus A2. For the second case, the cost would be D2 plus A2. So ND2 equals minimum of these. So this in this gives us an intuition to store a variable while you're iterating from left to right. So or we can define this in we do not need to store a variable also. We can just do ndi equals min ndi minus 1 plus ai comma di plus ai. In the first case, we move right from the previous cell. In the second case, we go down from the upper row. So we have our transition states to transition from DP states of one row to the next row. We do this for each uh, rotation, and for doing L rotations, we have to add a cost of LK also, because one rotation costs us K units. So finding this DP for one rotation takes order m times, since there are m states and there are m rotations. So finding this takes order m square times for each rotation. And since there are n rows, finding the DP value of each row takes order nm square time. In the end, we just output DP of final row and final column. Since nm is bounded by 5 before and m is bounded by 200, summation of nm square is bounded by, which is enough to pass within the constraints. This is my code. It is very short. First, we take the input matrix. First, we take the input. We initialize the DP for the dummy row in the beginning. DP00 equals 1 and rest all to infinity. Then we iterate over rows from 1 to n. Then instead of doing transition from previous step, I used a previous state, I used a dummy variable. I do cur equals when cur plus aij when I transition from the previous cell in the same row, or I transition from the same column from the previous row. For that we have this dp value. And then I do dpij equals when this. Then for the next rotation I rotate the array a. Here variable ad stores the value for here the variable ad stores the cost for rotations for the current row. Okay, so let's do problem E now. This is an interactive problem. We are given an array which length is a power of 2, and we have a hidden integer k. The given array A contains exactly 1 1 and remaining all zeros, and we do not know where the 1 is. And we can input queries to the interactor. We can input L, R, and first it finds the subarray sum S L, R in the array that is it has. And if the subarray length is less than k, then it outputs us the subarray sum only. Otherwise, if the subarray length is greater than equal to k, it outputs 1 minus the subarray sum of that subarray. So we have to find the value of k using at most 33 queries. So the key info here is that there is exactly 1 1 in the array and remaining all are zeros. And also observe that n is greater than equal to 4. So this idea for this is first we divide the array into three parts of length floor of n by 3. Like we don't consider the remaining part right now. So let's say the array is divided into three parts of length array floor of n by 3, and then there's some remaining part here. We ask the interactor the subarray sum from for these three subarrays. If at if none of them is 1, then we know that this must be 1. So let's start with the other case. If multiple of them are 1, then we know that k is less than equal to floor of n by 3, because if multiple of them are 1, that means the interactor is giving us the opposite output, because there is exactly 1 1 in the array. So let the output for this be x1, and this be x2, and this be x3. If x1 plus x2 plus x3 is greater than equal to 2, implies that k is less than equal to floor of n by 3, because this means the interactor is lying. And if the interactor was lying, then also this holds that x1 plus x2 plus x3 should be greater than equal to 2. So this is a bijection. So if x1 plus x2 plus x3 is less than equal to 1, implies that k is greater than floor of n by 3. Let's consider the first case now. In this case, in whatever array it outputs 1, we know that there is no 1 there because it is lying in that array. I mean, the interactor is giving us the incorrect output for that subarray. So let that subarray be L, R. Then we have to binary search over K in the range 0, n by 3. For that, we pick any length m. For that, we pick any subarray in this range of length mid. If the output is, first we know that there is no 1 in this subarray. So if the output is 1, that means k is less than equal to mid. Otherwise, k is greater than mid. So handling the first case is simple. Now consider the second case. In this, if any subarray gives us output 1, then we know that the 1 lies in that subarray because the interactor is telling us the truth. Otherwise, if the sum is 0, this sum is 0, then the 1 lies in the remaining portion. So we have to binary search over k in the range floor of n by 3 plus 1 comma n. So this all elements in the range are greater than the lengths of any of these four regions. So for checking each region, for checking each value mid, first we like find the subarray which contains the one. Then we can enclose the entire subarray which contains the one using a length of subarray which has the length mid. So we find such a subarray which encloses the sub the one of the four subarrays which has the one and query that subarray. So our query will be one. Query output will be one. Output equals one if interactor tells truth, implies k is greater than mid. Otherwise, if it is zero, that implies then that k is greater than equal to k is less than equal to mid. So again, we can binary search for the second condition also. So initially, we take three queries for these, and the binary search requires us at most 30 queries because the length of each subarray would be because n is less than equal to 2 to the 30. So in total, we take at most 33 queries, which is required. We have to find k in at most 33 queries. Okay, so this is my code. First, I take the input in. Then I found the length of the array subarrays that we output in the beginning. That is floor of n by 3. Then I query for three consecutive subarrays of length n by 3. Then I input their values. If the sum is greater than equal to, then we have to binary search over range 1, floor of n by 3. Initialize answer with len. Then I output this. Find a subarray. Then I query a subarray within a subarray which does not contain a 1 and update my variables accordingly. And similarly, I binary search for the other case. That part should be simple, I think, if you got the idea. So that's it for today.